So lecture 6, we start with sequential circuits. We will talk about the flip-flops concept. Lecture 6 is starting to have a different type. Sorry. We will have different type of hardware, which is sequential circuits. We start from this lecture, I mean, from this lecture on, we will speak about different type of hardware, which is sequential circuits that can remember the previous states. Is different from the combinational logic, which is not remembering anything. The output depend entirely on the input. But for the flip-flops and sequential circuit, the output depend on the previous state on the input and the previous state. We'll talk about this in detail. But what I want you to understand right now is to understand that we will move to different type of hardware. So we'll talk about the sequential circuits. We'll define latches, flip-flops, and the problems which is happening in the sequential circuits.
Doctor,
Yes.
Doctor, is this chapter 6 like it was for the last week or no?
Yeah. It's this. This should be the last week, but yeah, it should
Yeah,
be.
but it's this one, right?
Yeah, this one. Not
I was just
is
asking.
not is not new subject. Is the same.
So only on the YouTube, the chapter 5, and this is chapter 6, right?
Yes, exactly.
Okay.
I didn't
Thank
add
you, Doctor.
anything because I thought I said okay, you just give the
Yeah, Doctor,
lecture.
in this way, better actually.
I know, I
In this
know.
way.
It's better to have little things you understand them deeply better than having many things that you don't understand.
Yes, Doctor.
Okay,
Thank you so much.
okay. And for the combinational circuits and sequential circuits, we have a difference between the combinational circuits and the sequential circuits. The block diagram of the combinational circuits is simply like that, is like a black box. We have an input, we have output, and we have M inputs here, and we have M in outputs, and the output depend entirely on the the output depend on the input, only on the input, no other thing, just on the input. You just have an input, and then you will have an output. You change the input, the output will be changed accordingly. No states, no feedback, no cycles. We don't have cycles, we don't have feedback cycles, and so on. This is the combinational circuits. But in the sequentials, yeah, why we use the combinational circuits? Actually, we have interesting and useful designing arithmetic circuits for adders, for multipliers, or in other words, the data path of the computer. If we want to implement the data path of the computer, we should use a combination circuit. Doesn't mean that sequential circuit is better than the combination circuit. As I'm saying to the students always, we have two things. We can use one thing in its correct place and the other thing in its correct place. It doesn't mean that one is better than the other. It means which place should I use the combinational circuit, and which place should I use the sequential circuit. We say, okay, because as a students at the beginning, if we see the word cannot remember, it doesn't mean it's a drawback. It doesn't mean that there is a drawback in the combination circuit. It's characteristic. It's characteristic. It doesn't mean that it is not. It is an artifact, or it is something bad. It is good. It is. Or it is not good or bad. It is just like it's a characteristic. Combinational circuit cannot remember what happened in the past. The outputs are a function of the current inputs. So as I told you, we have combinational circuits, we have sequential circuits. We use the combinational circuits in its correct place, and we use sequential circuits in its correct place. In certain cases, we might need to store some information before we proceed with our computation or take action based on a certain state that happened in the past. For example, the counter. I want to count from 1 to 10. So I count 1 and I should count 2 depending on the previous state, which is 1. So I add 1 to the previous one, which is 1 plus 1 will move us to 2. And then if I want to move to 3, I should add 1 to the previous state, which is 2. So adding 1 to 2 will move me to 3, and so on. So sequential circuits is important or capable of storing information. Okay, I muted I mute I muted the mic. Sequential circuits sequential circuits are capable of storing information between operations. They are useful in designing registers, counters, and control circuits. So the combination circuits are used for the path of the data path of the computer, and the sequential circuits are used for the control circuits. Here's an example of the how to understand these sequential circuits. We have a counter here. We have 0, 0. If we want to move to 0, 1, so we should have an input of 1 and output of 1. And if we have an input of 0, we will have an output of 0, and we will stay at the same state here, which is 0. If we have an input of 1, we will have an output of 1, and then we will move from 0 to 1, 0, 0 to 0, 1. Okay. So the counters is an example of the sequential circuits. You start to count to 0 and then proceed to count with 1 and so on. The counter is an example of a sequential circuit that need to remember the previous state in order for it to go to the correct new state. The output of the counter is based on the current state and also the inputs. It depends on the previous state and the input. For example, the ATM machine. The ATM machine is an example of a sequential circuit. You insert your card, this is state 0. The system will then go to state 1, which you will enter your PIN number. And then if you're successful, you go to state 2 that will ask you for which operation you want. You want to withdraw money, you want to determine your balance, whatever you want. This is a state 2. It's a screen that displaying the operations that you can do. Then the ATM machine will yet another example. The ATM machine is another example of a sequential machine that will give a correct response based on your input and also on the current state. Yeah. So this is an example of a sequential circuit, the counter and the ATM machine. Also, the control of appliances. The control of appliances is another example of the sequential circuit. So, for example, if we have a washing machine, the washing machine is an example of a sequential circuit because we have an initial state, and we wait for an input from the user. For example, the setting dials to perform a certain task. Based on the input and the current state, will move from one state to another, wash, rinse, spin, and so on. So the washing machine should start with filling the water. After filling the water to specific level, start to move and rinse and dry the clothes and stop. It's like that. So this is another example of this sequential circuits. We have taken three examples. The first one is counter, the ATM machine, the second, and the third is control of appliance. Sequential circuits. We remember If we remember the combinational circuit, that block is a combinational circuit, but we add next state with a storage element that that representing the current state, and this current state will be an input to the next state to get the next state, and so on. It means that we have a loop, we have a feedback here. The sequential circuits is simply a compilation circuit with a storage element that contain a feedback. Feedback that that means that the next state or the output depends on the inputs and the previous state. This is the sequential circuit. Information that is stored in the storage elements represent the state of the system. And this is the output will depend on the inputs and the present state. Okay, this is the type of the sequential circuits. We have two types of the sequential circuits: synchronous and asynchronous. Synchronous and asynchronous. Synchronous means that there is a global clock that controls the entire circuit. This is synchronous circuit. Asynchronous circuit, we have different units are controlled by different clock. So each unit has its own clock rate. This is asynchronous. But synchronous, we have one global clock that controls the entire circuit. So these are the two types of sequential circuits. Nurhan, is you asking for again for what? This slide? This slide or the previous slide? Okay, we have two types of, here we have two types of sequential circuits. Two types of sequential circuits. The first type is synchronous. Synchronous means that everything is working together. Everything is working together. So we have a global clock. The global clock means at each edge of the clock, all the units in the circuit will move to the next state. But for asynchronous means we have different components in the circuit, and each component has its own clock. This means that they are not synchronized together. They are working in different rates. One is faster than the other. For example, we have different units, and one is faster than the other. But synchronous means they are working at the same speed. They are working together and they are changing their states at the same speed. This is the difference between synchronous and asynchronous. I wish it is clear for you, Norhan, now. Okay. Okay. Thank you. Yeah. So we have here the synchronous type. We have a global clock. This is the clock pulse. Uh, it feeds the flip-flops, and this is the pulse, the clock that is fed to the clock pulse. At each edge, we can say positive or negative. The positive means that if we raise from 0 to 1, raising from 0 to 1, this is the pulse, and this pulse is going to activate the circuit and change the state of the circuit. And we wait till the next edge, which is this one, and this one, and this one, and this one, and so on. So the changes are occurring here at this exactly the edges that will hold the changes. It means that uh, at each edge we will move to the next state. at each edge. So for example, okay, let's take an example to make you understand that if these flip-flops are representing a counter. So at this edge we have 0, and the circuit will be at 1 at this edge, 2 at this edge, 3 at, it's counting, so it will change its state at at each transition from low to high, each transition from low to high. Okay, this is how the clock pulse is working. The first basic unit that is remembering, or it can store data, is latches. Latches can store data. We start to remember. This means that if you hear about the registers, these are the registers that can hold the data for a specific time. So the main building blocks of the registers are flip-flops. So flip-flops is advanced, but we start with the basic unit, which are latches. Latches is a basic storage. The idea is coming from the idea is like we have a circuit here. We apply a voltage. This voltage we call it TPD, and we want to keep the output volt to be stay there forever. We want to keep the output voltage. The idea is to make a feedback cycle. We have an output here 0, and then we return it back to 0, and then it will stay there forever, because this is just give an input, and the output will be 0. If we change the input 1, the output will be 1, and so on. But here, if we want to hold the 0 forever, we can make a feedback cycle. We can make a feedback cycle like this. We take the output and connect it to the input. This means we will have always we will have 0 here. But we need a circuit for this, so we can do that with just two inverters. As you know, we just uh, use two inverters because we need to keep the output the same as the input. If we have 0, so we will take it 0 again. But if we use one inverter, we will have 0, and the output will be 1, and the 1 will be changed to 0, and the 0 will be changed to 1, and so on. This is not good. We just may want to make sure that the output, if the output is 0, it will be kept at 0 forever, forever, yes, forever. So if we have 0, the 0 will come back here, so it is inverted to 1, then inverted to 0 again, so it will be 0, and then return it back from 0 to 1, from 1 to 0, and so on. This is the idea of a latch. It's like we have a storage element with a delay, time delay, that let us hold the value of the digital value for a specific time. But here we can replace the inverters with AND, NAND, and NOR gates because we want to control the logic of the circuit. So uh, we can make the same concept here, which has a feedback using this SR latch. We have the input here, we call it reset input, and we have the set input, which is this one. And we have here the Q, which is the previous state. The previous state will be changed to the current state. So this is the output, mainly the output. And this is the invert of the output. This is the invert of the output. If we have 0 here, this is going to be 1. If we have 1 here, this is going to be 0. And uh, you should understand the concept of NOR gate. So if we have X and Y for NOR gate, this is important to understand. This is Y. So if we have 0 and 0, this is going to give us 0, 1. This is 1, 0, 1. Is not a problem. The order is not important, but here we have 0, 0, and this is 1, 1, which is 0. This is NOR gate. This means if we have an input, okay, let me remember. Yeah, if one of the inputs is fixed to 0, the output will be changed or flipped. If the one of the input is 1, this means the output will be always 0. The output will be always 0. I want you to remember this idea, just because to understand how the NOR gate is dealing with the input. It means that if one of the inputs is 0, this means the other will be flipped, the other will be converted. So if it is 0, it will be 1. If it is 1, it will be 0. But for the one of the input is 1, is fixed to 1, this means the output will be always 0. Okay? So for example, here we have set state, reset state, and the undefined state. And we'll say how to get rid of the undefined state with different type of circuit. Uh, so here, the SR, if we take an example, we can take this one, this example. We have here the R at 0, and the S at 1, and the Q, which is the previous state, at 1. Now, we have 0 here, as we said that the value here will be converted. The value here will be converted. So if it is 0, it will be converted to be 1. Because we know it is 0, because this is the inversion of that 1. So it is 0, and we have here 0. This means the output, the other one will be converted to 1, because it is 0 already. And here we have the set input. This means the output will be always 0, independent of the input. Whatever the input here, the output will be always 0, because we know that this is the characteristic of the NOR gate. Okay. Okay, so I set the output at 1. This is the meaning of set. Set means keeping the output at 1. And reset means keeping the output at 0. So the output will be kept at 1 at the set state, and will be kept at 0 at the reset state. If I input 1 and 1 here, we will not be able to get a specific output, because we can say it will be high resistance or high amplitude value. It is not logic. So we should avoid entering 1 and 1. Okay, and we will have a solution for this problem by attaching the both input together. Okay, so basically, I want you to understand that we have the SR latch. We set the SR, means that we put 1 here. This will keep the output at 1, and the reset state means that if I put 0, this will keep the output at 0. This is the reset state. Okay. This we have explained already, and this is undefined. And this is the characteristic of the NOR gate that I told you you should understand. to be able to understand the logic diagram of the reset of the SR latch. Don't worry about the details of the SR latch. We will, after that, we will deal with SR latch as a block. We will deal it with as with a block. I will not concentrate on this part in the exams. I just want you to understand the basic idea of holding the data and resetting and setting the data, the output data. After that, we will concentrate more on how to, for example, how to create a counter, how to create a counter, how to make a counter, how to make a register, how to make shift register, and so on. This is the main. This is what I want you to concentrate on. Here, I just want you to understand the basics of resetting and setting the output. Okay, and here it will talk about another example. We take another example here. This one is means that the S is at one. If the S is at one, this means the output will be always zero. The output will be always zero. So the output will be always zero. And this is going to be flipped back to the input here. This is zero. And the reset, which is zero, together with that zero is going to give us one. And this is the output, which is Q, will be kept at one. The latches are storage elements that can maintain a binary state indefinitely, as long as a power is delivered to the circuit. This means we have the first storage element, which is latch. The latch can hold data for a specific time. Latches are asynchronous circuit. Latches are asynchronous. Asynchronous means that they don't have a global clock that can control them. Latches are used to build more complex synchronous circuits, such as flip-flops. So we cannot, as I told you, we cannot use the latch as a building blocks, for example, for the counter, but we can use flip-flops that we will study shortly. This is the timing diagram for the states. Here we have the reset. Here we have the reset, the set as zero. This means a reset, and the R at one, the S at zero, and the R at one. This is going to create the output, which is always holding the value of zero. Here, holding the value of zero. Also, if the value of R is changed to zero, even if the value of R is changed to zero, this will not affect the output, and the output will be kept at zero. The output will be changed to one only if the S is changed to one. If S is changed to one, this means we are setting the SR latch, and the value of the output will jump to one here. Here we have the undefined state, and I don't want you to go into the details because it is a different level of the circuit. Is not a logic circuit, is the transistors, the transistors level. They are not working because of the transistors level, which is not studied in this course. But what I want you to understand is that SR latch is not defined at the state of S is 1 and R is 1. We can make SR latch using the NAND gates. We should also know the idea of the NAND gate, and we should draw it. I think so. Here we have X and Y, and we have 0, 0, and 1, 0, 0, 1, and 1, 1. The AND gates means the invert of the NAND gate is invert of AND, so this is going to be 0, 0, 0, 1, so it is 1, 1, 1, 0. So if one of the inputs is 0, this means the output will be set. The output will be always 1. If the one of the inputs is 0, is kept as 0, this means the output will be kept at 1. Okay, this is the characteristic of the NAND gate. You have to understand it first before moving to the SR latch. The second one is means if we hold the one of the inputs at 1, the output will be flipped from 0 to 1 and from 1 to 0. Okay, uh, uh, putting that in our mind, putting that in our mind, we can move on to understand how this is happening. So if we have Q at 1, this is the previous state, we call it the previous state, and we have S at 0, so, sorry, return it back to, okay, sorry, we start from the, yeah. So this state, which is 0 and 1, 0 and 1, as we know that 1 means what? I I should write it back because I confuse between the NOR and NAND, so I have to write it back. 0, 0, 0, 1, 1, 0, and 1, 1. This is NAND, which is 1, 1, 1, 0. When we have 1, okay, let me write it out here. If I have 1, we have converter. If we have 0, the output will be always 1. Okay, I have written it on my paper here because I should remove it back because to move the slides. So we have 0 and 1. If we have 1, this means we have a converter. Uh, we have a converter for the output. If we have 0, this means we have always 1 independent of this value. This means we have 0 here. The output will be immediately 1 because it is not depending on the input here, because if we have 0, the output will be always 1. That's why. So the output will be 1, returning back the output to this gate. And we know that if we have 1 at one end, the output will be the conversion of this value. This value is 1, the output will be 0. Okay? For the 1, 1, this is the resetting state. If we have both of them at 1, this means the resetting state. Okay? Let's just take the 1, 1. But the undefined is happening in different place here, which is 0, 0, not 1, 1 as a previous happened with the NOR gate. Okay? Latch and control. If I want to control or make a control means I want to control the output of the SR latch. I want to have, for example, I want to have the SR latch setting or resetting, or valid or invalid, means that I want to control the states of the SR latch. If I want to control the states of SR latch, I should have another level of NAND gates. This is the first level that we have previously defined. We should have another level of the NAND gates, and we can connect the the control to the NAND gates here. And if you remember what we said about the values of or the characteristic of the NOR gate, if this is 0, if this is 0, this means the output will be always 1. independent of the input, and this is the this is not the undefined, but the if this, because the undefined is 0 0, not 1 1, because the undefined is 0 0, as you see. So if I put the control to be 0, this means the output will be always 1, which is 1 here and 1 here. And we can we can have we can have another state if we use the control at the control this control, we put it at 1. This means it converts the s to be 0. If it is 0, it will be 1. If it is 1, it will be 0. And r, if it is 0, it will be 1. And if it is 1, it will be 0. It depends on the control value. So if the control value is 0, if the control value is 0, this will be no change in the output. No change in the output. If the control if the control is 1, this means this is a previous, exactly as we studied before, the previous state, the previous SR latch. Okay, I mean, if we have a control here, the control at 0, this means no change in the output. But if we change the control to be 1, we will get the previous studied SR latch, the same. Okay, 0 0 will have no change. 0 1, this are a set state. 1 0 is a set state, and 1 1 is undefined state. Okay, but here I don't know. The 0 0 is undefined state, and here it says 1 1 is the undefined state. Okay, yes, this is because the adding this layer is making different from that one. Adding this layer, it doesn't mean that it is exactly this one. It is different. Okay, uh, that's yeah. So the undefined will be 1 1 here. So you just remember SR. If it is 0 0, no change. If SR both at 0, there is no change. If S is 0 and R is 1, this is the reset state. Means that I am making S at 0. This means the output is always 0. And if I put S at 1, so 1 0, it is going to be the set state. So I want to keep 1 at the output here. And 1 1 is the undefined state. Okay, I just want to make sure that you understand this part. Again, I will say it again. We need it in the flip-flops, so I will repeat it again. If we have the SR at 0 0, this means no change, means the previous states will not be changed. If it is 0, it will be always 0. If it is 1, it will be always 1. And for the 0 and 1, this means a reset state. Reset state means that I will hold an output of 0 forever. And for 1 0, this is the set state, and I will hold 1 for forever or for a long time. This is the set state. And if I have 1 1 at the input, this is the undefined state. Okay, to make sure of the problem of undefined, okay, I should connect the S component to an inverter So I make sure that I'm working only with the required states, which is 0, 1, and 1, 0. These are the required states that I want to concentrate on. And that's make the truth table of the SR latch is simpler. We call we call this latch as D-type latch. And its implementation is very simple. So if we have a control set as 0, no change of the Q. If we have 1, 0, sorry, if we have 0, it's like that. It's not, we don't look at control. Control means that the circuit is working. So if we have 0 as D, the output will be always 0. If we have 1 at D, the output will be always 1. And that's the objective of our implementation of the sequential circuit. We want to keep values. We want to keep value for a long time. Here we reach the desired circuit that we need. We put 0 here, the output will be always 0. We put 1 here, the output will be always 1. We keep the value for a long time as much as we can, as we need. So this is the first register, which is the D-type latch. But we studied the SR latch because we want to understand how the logic is happening here. Finally, we get to this final circuit, which is the best one compared to the SR latch and the previous ones, because it gives us the required function exactly as we want. We want to hold 0 or 1. We put D as 0, so it will hold 0. We put D as 1, it will hold 1 in its state. Okay? No illegal state, because we are sure that the input will be all either 1, 0 or 0, 1. There is no other states here, because one of the input is going directly to this part, and the invert of the input will be going to the other part. So I'm sure that there is no illegal states here. There, sorry, there are standard types of the symbols that are used for the latches. This is a symbol for the SR latch, another symbol for the converter of the SR latch, D with 1 control, and D with 0 control. This is should be 0 control. Yes. And this is the drawing of SR latch. This is the SR converted. And this is D with 1 control. And this is the negative. This means the negative of the control. Okay. It's 1 control means that one line of control, I think, is not logic 1. So it's okay. Issues with latches. We have some issues with latches. We should understand the problems that happening with latches. The transparency of latches. What is the transparency of latches? The state of latches allowed to switch by a momentarily change in values on the control input. As long as C, the trigger is high, state can change. This is called transparency. I will show you in detail here. I will show you the detail. I want to have an example for this transparency. Yeah. The output of one latch may feedback to the another input. As soon as the input changes, shortly thereafter, the corresponding output changes to match it. Mm, okay, this is the transparency combination. Okay, the final statement. Okay, let me give me a second. Okay, okay, returning back to the transparency. Uh, the transparency means we have an input and the output will be directly happening on the we have an input, we have a specific input, and we have the output will be immediately happening or uh, apparent on the output. This is the transparency. So if we have an edge here, uh, the transparency means that we are working on that level, means the output will be kept at the same state as long as the value is 1. But I want to just work on this edge. We want to work on pulses. Transparency means as long as this is 1, the output will be remaining, or the output will depend on the input. But I want to just change the output on the edges, on these edges, not keeping the output for a long time like that. I want to change it immediately. For example, I want to change from 1 to 2 in the counter only once here. Okay, I want to change or to swap or flip the values at the edges. I don't want to have the output staying at 1 for a long time. I want to flip the input or flip the state from state or change the state of the circuit from state to state at the edges. Okay, that's the uh, this is control C that we have seen with SR latch. It is 1 or 0 as we have seen. It will be kept like that. But it is not even like that. It is just like that. It is 1 or 0. It will be always 1 or always 0. This is the control. I want to change at a specific time interval, not to have the control like that. That's why we need to have another type of circuits. We need to have, we don't need to have the control line like that, like that line, this one, control line. We don't want to have that control line. We want to have a clock, not control. We want to have a clock because I want to change the states at a specific time intervals, at a specific time moment, not interval, moment. I want to change at specific moment. That's why the control is not working with us. We should have the clock. That's why we should work with the flip-flops. Okay, we should work with the flip-flops. So the flip-flops ensures only one transition. So the transition will be happening at this edge. We have two major types, master slave. This is level triggered. The level triggers if we have the level of 1 or level of 0. And the edge trigger means the transition from 0 to 1 or the transition from 1 to 0. This is edge trigger. So we have two types here, the master slave and the edge trigger. The master slave is level triggered and the edge triggers is happening, or the change is happening at the edges, either the transition from 0 to 1 or the transition from 1 to 0. This is the first or the first flip-flop that you may see. Uh, it is implemented by using two SR latches, and we take the input, the control or the clock rate is coming from the input. Yeah, from the first one is inverted to the second one. This means one of them is working, the other will be not working, and so on. One of them is working, the other will not be working because the control here will be zero, for example, here will be one. This means this will be disabled and this will be enabled. This is a master slave SR flip flop. This is the master and this is the slave flip flop. When the master is enabled, the slave is disabled. The output Q will not change when the inputs change. Because this way, uh, we have transitions from S to Y and from Y to Q. This is not transparent, as we know, or we hear the expression of the transparency. This is not a transparency because, you know, S will be transparent with Q. We will not have S directly as an output to Q at each edge, but we should have that at a specific time interval because we have one of the circuits are enabled and for example, if this is enabled at the first time, the input from S is moving to Y, and then after this is enabled, the input of Y will be moved to Q. That's why this is master slave means it is not transparent because it is not transparent because the output Q will not depend entirely on S directly. I mean, if S is the input, Q is the output, Q will be apparent, Q will be reflected, will not be reflecting the input immediately because we have a transition state in the middle. Here is a timing diagram of the SR latch, of the SR, sorry, the SR flip-flop, the master slave SR flip-flop. We have, this is a control at one. This means this is going to work, this or enabled, the other one will be disabled. We trace the behavior like that. We have here the control at one and the S at one. This means the output will be one. Okay, the output will be one. So Y will be one, and it will be hold there. It will not appear on the output Q immediately because this is disabled. This is disabled. So Y will be hold here. The value of Y will be hold here. Now the control is changed, or the clock is changed to zero at this level of zero. This means this is disabled and this is enabled, and the value of Y, which is this one, will be moved to the output, which is Q, at the next level. This means, returning back, the value of S will be or the Q will have the value at the different levels. We have level here which is high and the other level is low. When the level is changed, we have the output. The output is appearing. The output is appearing and is effective at the levels, not at the edges. Okay. Okay. I think it's time now. What's time? Okay. Uh, are you with me? You're listening to me? I should enable the mics again. Hello, participants.
Yes, doctor.
Hi guys. You listening to me?
Yes, doctor.
Okay. I think it is sufficient for today. We continue these slides in the next lecture next week, inshallah.